Thank you, everybody, for joining us today. This is actually a modification of a talk I recently gave at Day to Day Texas down in Austin. And there was a lot of interest in the topic in general around declarative data pipelines and how we create this autonomous control plane. And so we've packaged up a lot of the themes here and even given them a nice little revision as well. As it's a pretty interesting set of topics and goes pretty deep on the technology at Ascend and frankly on control planes in general. So we really hope everybody enjoys the conversation here. A quick walkthrough of the topics that we're going to touch on very, very quickly. First, we'll talk through some of the key pipelines that are key questions that we have to answer when we build data pipelines to begin with. We'll highlight where there's really this missing technology and then start to walk into more of the trade-offs between imperative and declarative systems. And then very quickly, we're going to get into the meat of the conversation, which is building of this control system and how we properly support declarative pipelines. So let's get started on that. Quick background, I think many people on the webinar are familiar with Ascend. We are a roughly 4.5-year-old company based out of Palo Alto, California. And the shortest version of it is we absolutely love data pipelines. Most of the people in the company, we have been building data pipelines for long portions of our career. I actually wrote my first data pipeline, my first MapReduce job back in 2004. And I've really been building data pipelines and teams building data systems ever since. One of the most interesting, exciting parts of my journey was it was really exciting in the last company I founded when we crested through the billion event per day mark, and we're building high performance, high velocity systems to process and scale to that volume. And it's funny as we look across the last few years and the growth of data volumes in the industry, and it's no longer does 4 billion data points a day seem as exciting as we've already crested through the trillion data points and trillion events per day mark for Ascend. Now, one of the really interesting aspects about this, however, is I would contend that the scaling portion of how many events, how many records per day is no longer actually the biggest challenge. Instead, it's how do we enable more people to build more data pipelines faster and more easily? And to do that, that's really comes down to a very different approach, which is how do we build these smarter pipelines with less code? And that's where we're going to spend most of the time today talking about what is this intelligence layer that we actually are really looking for that gives us more leverage as data engineers. Now, when we're building data pipelines, oftentimes it gets, we start with this very simple vision of we just have some data coming in, it's sitting there in S3 or Azure Blob Store or even in a Kafka queue, and we want to propagate that data through our system. And the logic that we want to apply to it is pretty simple. But there's a big misconception as to where we spend most of our time as data engineers. And today, it's really not spent on the data logic itself, but it's instead actually answering and then codifying these questions, which is, when should I run my code? Did I already run my code on this piece of data? And if so, is it safe to run it again? Or do I need to run it at all? Moreover, one of the things that happens in most big data systems is we introduce change. We're changing the data, the code is changing, and as a result, there's really big questions that are raised as to should I rerun my code on some or all of my data? And all of this then compounds in the complexity grows exponentially. And when we start to think of that was just one set of data that we ran one transform on, when we move that data and we propagate it through the rest of the business, how that data was used downstream and where that data went and what was done with it conflates the problem even further. And so as a result, we end up usually in this common data pipeline architecture that looks something to this extent, which is we're feeding a bunch of downstream systems for data science and BI and ML. And we start with this notion of we're going to schedule some logic on data, and we're probably going to send it down to Spark or maybe Hadoop. And we'll store a bunch of the intermediate data inside of a blob store. And this is a pretty common architecture we see across a lot of customers today. And when we start diving in with teams, and we've done a bunch of this research, and it's funny because we always start with this notion of just really simple data logic. And then very quickly, the time investment starts to shift towards all of the things around it that are required to just simply make things work, make your pipeline work at big scale with the modern big data technologies. So things like checking for new data, formatting it properly, tuning the Spark engine, handling the inevitable errors that may emerge. And this is really the first wave of stuff around your data logic that you start to go build. Then we get into the second stage, which is really oriented towards how do I make my system more efficient? So we start to build sub-modules to our pipeline engines that profile the data, figure out how do we incrementally process data so we move smaller pieces of data through with more efficiency. We start to look at how do we persist intermediate sets of data so we're not reprocessing and doing the same work over and over again. Then even start to figure out how do we dedupe work. And eventually we get to this third stage, which is, hey, we've started to build all these pipelines that are moving all of this data around, and we have more and more engineers touching more and more data. Now we need to know whether or not we can trust that data. So we start to build a lot of systems around the auditability, checking for the data and the code integrity. We start to track lineage and apply layers of security and governance on top of our data pipelines. And really quickly, we start to find that the vast majority of our time is not actually spent on the data itself, but is instead spent on the stuff around it. And it's orchestration. And this was a really interesting insight for us at Ascend when we started the company, which was, gosh, something is really different. Because in the previous generations in our careers, when we were building data pipeline, or when we were working with data pre-pipelines, we could put all of that data inside of a database or a data warehouse. And we could write a query. And this magical 3 lines of SQL could produce some pretty phenomenal results. And the reason is because it's sitting on top of millions and millions of lines of code that were built by brilliant engineers at MySQL and Oracle and Teradata and everywhere else that give us a database engine and a query planner and a query optimizer. Yet there's a missing piece of technology here when we think about data pipelines. A lot of what a database engine does when it's pulling data out of the underlying storage, a lot of this burden, the converse of it in a push-based construct when we're building data pipelines, this burden now falls on us as engineers. There is no pipeline technology. I have storage technologies, I have processing technologies, but there isn't a pipeline technology that offloads this burden for us. And as a result, we're manually designing these query plans. The push-based equivalent for pipelines, we're designing these for each and every single stage of every pipeline. And this is one of the reasons why these systems tend to be pretty slow to build, and why we as engineers invest large amounts of time just writing the code around the actual data logic is because of this. And so we took a bit of a step and said, well, let's look at the evolution of pipeline orchestration across industries, both previous generations and current generations, and look at how things have evolved over time. And before we dive into this more, we actually have our first survey that we're going to do, which is for the audience here, really curious, just gonna take a minute. Which of these orchestration technologies do you currently use or have inside of your company today? And would love to see what you have. All right, okay, great. Well, those last few votes trickle in. We'll highlight, so one of the really interesting things that we've seen across industries is we've continued to really invest and build smarter and smarter orchestration tools. We started with cron, things evolved from Luigi to Uzi to Airflow, and what we've seen, oh wow, and we have really good results off this too, which is a pretty interesting spread of use cases here. And what we've seen is those technologies have evolved into these 2.0s. And the 2.0s, whether it's traditional technologies like Talent and Informatica, or some of the new cloud versions like Glue, Data Factory, and Data Fusion, they adhere to similar paradigms in the sense that they're schedule-based, they're imperative, but they expand the addressability and the accessibility of these products by hosting them for you by giving low code or no code options to how you can actually design pipelines, and you get some really nice templatized code generation as a result. And so what we've seen is, and obviously we believe that there's a third generation on the way, and what we've seen is that there's the opportunity to create a different paradigm. We can still benefit from a lot of the investments and the advances of the second gen systems, but we can now, as the industry is maturing and we have better understandings of how pipelines work and operate and behave in the real world, there's a good opportunity to take this paradigm and move from imperative to declarative systems. And the promise of moving from imperative to declarative is a pretty common one that we see across a lot of technology domains, and ends up introducing some really powerful benefits that we'll walk through in a bit. And so when we were going through our journey at Ascend, we started to spend a lot of time thinking through, well, what are some other good examples of declarative systems out there, and what can we learn from? And so we started to look around for some other ideas. And this is, I think, going to be our second survey. And we looked across a bunch of different industries to see what other types of systems are out there today that people are using. So another quick survey just to see which of these technologies, whether you use them directly or are being used inside of your organization today. And we're trying to see the overall level of popularity. Some are obviously very popular and others are more emerging. This will give us a good sense of who's using what today. All right, so we got a bunch of votes on that one too. And so obviously these are all declarative technologies, and they have a tremendous amount of potential and power and capabilities to really accelerate our efficiencies as engineers across domains, whether it's infrastructure for Terraform, for container orchestration, for Kubernetes, for React and front-end engineering, and obviously databases, and SQL is a very declarative language that's been popular for a long period of time. And when we think about the sort of fundamental notion of declarative and imperative paradigms, the very academic definition of this is declarative programming allows us to express the logic of a computation without expressing the actual control flow of it. The reason many invest in declarative models is it does minimize and or even eliminate the side effects and create simpler, more sustainable systems. And this is a very academic review of it, but put a very different and direct way. Imperative versus declarative is about describing the how versus the what. And this is a really simple framework to think about how we build these systems, because oftentimes we end up with very different results when we try and get too far deep in the weeds on a system versus really just focusing on those end results. And so when we think about some of the pros and cons of imperative versus declarative systems here, imperative systems are almost always the first wave of technology we see in industry. The reason we see this is because it offers a high degree of flexibility and a high degree of control, and there's a lot of burden that comes with it, a ton of things that make it harder, but in emerging spaces where there aren't well-formed patterns and best practices, and frankly, just the space hasn't been around long enough to have sufficient investment. This is usually where it starts. Where we see a lot of industries move over time is to this notion of declarative. We find the patterns, we find the commonalities across systems that allow us to actually create a system that describes more of the outcome, the how, as opposed to the steps, the what, as opposed to the steps and the how. And as a result, we do find the benefits of less code, faster dev cycles, simpler systems that adapt on their own, and as a result are less maintenance. The catch here is, of course, you have to have a domain-specific control system. And so what we're going to spend some more time on now is how do we actually build that domain-specific control system, whether it's Ascend or whether it's something you may aspire to go build on your own. There's the same sort of fundamental core tenets that you really want to adhere to. So let's go do a slightly deeper dive into how this works. at a high level, when we think of evolving this orchestration paradigm, we've taken the approach of really looking at how do we not have all of this code that we're writing be on a schedule and essentially be under the control of this scheduling system, but instead, how do we invert the paradigm? How do we get the code that we are writing as engineers to sit on top of the stack and instead be describing and architecting what we expect the state of data to be and push all of these other elements into this control plane? And very simply put, this is sort of the base framework of what has to sit inside of this control plane. And when we first started Ascend, we honestly felt a little bit more like this, which was, we know there's a lot of things that sit in the middle here. And frankly, we just had to go do a lot of research and spend a lot of time trying to figure out what we wanted to actually be in there. So we surveyed a lot of folks. We spent a lot of time on whiteboards, and we came up with a ton of different ideas. A lot of the things that, frankly, over the last decade plus, we had been writing and doing on our own. And what we found was, as we started to really compress everything into this notion of a control plane, there was really three common themes that emerged that really helped us create a strong sense of structure. Those were a system that control plane has to be data aware. When we're writing pipelines, we have a lot of assumptions that we're making based on what we've seen be the behavioral patterns of the data itself, and we're baking those assumptions into the system. And so we can offload that if the system itself becomes data aware, and we'll talk more about that. The second thing that it needs to be is autonomous in nature. We want it to dynamically respond and react to changes in the ecosystem. If we can do that, then we don't have to get paged at 3 a.m. to increase the memory that we're sending for the JVM so the Spark job stops only, for example. And then the third one is intelligent persistence. We spend huge amounts of time as data engineers trying to figure out how we, in essence, proactively cache data and persist it along the way so our pipelines are faster. And the control plane needs to be able to figure out how to do that for us. So these were the three core elements of it. And what we found was this started to fit into a really nice construct. And we'll go back to this pretty frequently through the rest of the talk, which is we find that the world really does start to break down into three basic layers, which is the logic plane. This is where we as engineers and architects operate. We're defining the what and what we expect out of the data. And we're writing our code and we're submitting our configurations in order to do that. The execution plane down at the bottom is what we've had for long periods of time. This is our object store. This is our Spark infrastructure. It's whether it's I'm running it on EMR or Databricks or Qubole or CloudProc. It's our processing. It's our massive distributed chipset. But it's the system in the middle that connects those two. It's the control plane that determines how we deliver on the what by sending the work down to the execution plane. And so this is really where a lot of the magic ends up happening. So to come back to those three things that really make this possible, the first one is data aware. The system must fundamentally know about all data moving through the system for all time, including the profile of the data, where it came from, how it got there, where it went to, how it was used, and why. It sounds like a lot, but it's incredibly important because this is what we implicitly are doing as data engineers. When we're writing code for this, we're baking those assumptions into our system. So if we can offload that to a control plane, that makes our life a lot easier. The second piece is autonomous, as I mentioned. It needs to be able to continuously watch and change for changes in data or code and dynamically generate those tasks and the parameters that go to those tasks automatically for us. And there's a big difference between automated and autonomous. We'll spend a bit more time on that. As autonomy is beyond automated, it actually can change and adapt on our behalf. Then last, intelligent persistence. We talked a bit about, which is how do we make our pipelines faster and more efficient? And this is where we spend a lot of time tuning on our own. So let's go into more of how does this work? When we think about data awareness, just a reminder of those key questions we highlighted before, which is these are the things we must answer and then codify for every stage of every data pipeline. And we're going to come back to these 6 questions and highlight how does a data aware system help answer this. So when we think about data awareness and really knowing what's there today, most systems that are out there, scheduling-based systems, will operate at this notion of a component level. It is a block of code, a definition of some source data, and it will track the location of the data, the code that's running. But we've taken this a step further, and we've taken this down to be truly data aware and understand the fragments, the individual slices of data, the partitions that belong to a component. We keep track of a whole lot of data and the entire set of fragments that underpin each and every single component. And there's a few really important things that we track. First thing that we track is the data profile. We understand the schema of each and every single fragment. We know the min and the max of the fields, which is incredibly important downstream. And we also track the field lineage. We know where one field in that data set came from and why, what the transformations were applied to do it, and obviously then the converse of that, which is where it went. The other thing we track is the job that generated each and every single fragment. This is really important too, as we need to know where did the data come from, where did it go to, what was the SHA of the code itself, so we know if the code changes, the resources required, how much time it took to process, what engine processed it. We track all of this information because this is incredibly helpful to be able to use downstream. Now the last part, and this is, I'd say the importance of this is not proportional to the pixel screen real estate that's applied, but we'll dive into this more, is this notion of a PSHA. The PSHA itself is a unique fingerprint, a hash that we do that is a recursive hash of all of the code that has been applied to a piece of data or a collection of data, all the way up to the data SHA itself of the data. And this is a really important definition, as it allows us to create a very, very clear understanding of each and every single fragment. When we look at the PSHA, we can determine whether or not it's valid. And when we think about a declarative system, knowing whether or not that PSHA itself is valid and comparing it to the existing code and the existing data is incredibly important. And so the part of the magic of how a control plane works is being able to look at the existing state of data, the expected state of data, and figuring out if those match. And if they don't match, then figuring out what has to get done to make it match. So when we think about this notion of a PSHA, simply put, for a source piece of data, it's just the data SHA. But as that data propagates through the various systems, the PSHA changes and is morphed to be the SHA of that original plus the SHA of the code that's been applied to it. And what causes a PSHA to change then as a result is a number of different things. If I change the definition of a component, its PSHA changes. If I change the inputs of a component, or even of an individual fragment, just an individual partition, which may have just a few upstream partitions for it, if any of those change, if a new fragment shows up, that is now an input to an existing partition. If a fragment gets updated, if a fragment gets deleted, the inputs have fundamentally changed. And as a result, the PSHA itself changes. And our system then can detect that there must be something that needs to be done. For those who are paying really, really gruesome level of attention here, one of the big questions is, how do you know the inputs? When we think about a individual data set that is being generated that may have thousands of partitions, how do we know what the inputs are for an individual fragment? Because I may have 1 million input fragments that are going into 1,000 rolled up input fragments through some complex transformation, but I don't want to reprocess everything. I only want to know if one of those individual fragments has changed. And this goes back to what we highlighted on the previous slide, which was the data profile. Once we're able to actually profile the data and our system is aware enough to understand the SQL and the code that is running on the data, we now can do direct lineage tracking, not just at a component and at a logic level, but down to the data level itself. And this is what helps us offload a huge amount of that work. So let's go a little bit deeper here and talk through what happens. What happens when, for example, a connector changes? If I'm reading data all the way from a source, it's really interesting. If I make a change, the system immediately goes and checks for new and existing fragments, figures out if it already has them, starts to ingest and profile them. It'll figure out how to garbage collect the unused fragments in the background. And then part of the magic is, because that connector changed, all of the downstream components also have PSHA changes, and they'll start to automatically propagate those changes for us. Similarly, if a transform in the middle of a section changes, we get a similar benefit. Same thing as what happens up top, which is, or upstream, which is the system just starts to check for existing fragments, determines which for these fragments may be missing and need to be created. And as it does that, and as it backfills it, will automatically propagate that down as well. And this is the great part, is it works whether it's part of a new transform that's being created or even a change to an existing one. The PSHA logic happens the same regardless. So when we go down to individual fragment level, you'll see that the way that this really starts to work is when a new input fragment changes, we start to profile it. If it's a new fragment, we know that there's very likely to be some downstream fragments we have to go create, and there may even be some existing ones that have to be updated. Moreover, there's an update or a deletion to a fragment. Those propagate through pretty easily as well. And we'll find the same pattern happens when we transform those fragments, or when we do a transform fragment SHA in the middle as well. So let's pop up a little bit more now and talk about how this works when the system starts to detect these changes. Well, as we highlighted in the previous two slides, it's pretty straightforward. Once we know that there's a PSHA mismatch between what exists currently in the system and what needs to be there, we can really quickly and easily just start to generate the work to fix that. Now, the way this ends up answering our questions then, if I go all the way back up to those questions we had before, we recall these are the core 6 questions that we as data engineers have to answer that we're hoping now we can push down to this intelligent control plane. Well, by being data aware, there's a question which is, when do I run my code? And the answer there is pretty simple, which is we should just continuously evaluate. As fast as we can loop through the various data flows, we should be constantly checking the PSHAs and seeing if something doesn't match. And if it doesn't match, then we can quickly iterate through. The next 4 become really interesting, which is, did you already run your code? Do you need to run it again? Did any data or code change? The answer to these 4 questions all is the same, which is we simply check the PSHA. And this is part of the beauty of having a control plane, which is once it's data aware and has all of this logic, answering these critical questions becomes as easy as, does it already exist? And if it doesn't, we should generate it. And if it does, we don't need to do any work. Now, the last part is pretty easy too, which is, how is this data used downstream? From those previous slides, as we already highlighted, it's pretty easy then to start to traverse the graph and just look for more mismatched PSHAs. And so it's a pretty simple exercise once we have all of this metadata and this notion of the fingerprinting to determine whether or not we have the right data. So that's the recap on the data aware piece. Now let's go to the second part, which is how does this system itself operate autonomously? And there's really 3 components to the autonomy. First one is the ability to run continuously. And we're not going to spend very much time there as it's pretty straightforward. And frankly, if you can run efficiently at scale, which is the second big piece, it's pretty easy to then just continuously loop through and constantly checking the state. The third part of autonomy that we won't cover today, as frankly, it's an entire tech talk in and of itself, is how do we adapt to environment changes? We have all this metadata we're collecting. How does the system do really smart things like dynamically adjust how many resources it sends to Spark or how many executors it requires? All of those things we'll get to in a subsequent talk. But let's talk more about how we run efficiently at scale. And just as a recap, when we think about scale, we think about it on the order of trillions of records per day, monitoring billion-plus partitions, individual fragments of data that we're tracking the lineage and the connectivity of. And for us, this means how do we actually scale to orchestrating and maintaining all of the work that can be done by over 1 million Spark jobs each and every single day. And those are some of the really interesting and fun challenges. So diving into these, the 4 areas that are really interesting to running efficiently at scale is, well, first, you have to detect changes efficiently. Second part is you need to do less work. You want to be really smart about the work that you do actually send down to the systems. Third is you want to do the right kind of work. And fourth is making sure that you're intelligently managing both the workload and the capacity, and that those are pretty tightly mapped together. So going to the first piece around detecting changes efficiently, if everybody probably remembers this diagram from before, how do we do this? Well, if we overlay how we think about the structure of data itself, down at the fragment level, we have these individual fragments that are actually rolling up to time series partition data, for example. And one of the things that we know is we know that the December 31st, 2019 fragment from component B depends on its upstream component A's comparable input fragment. This would be in a map style operation. Well, one of the ways where we can do this really efficiently at scale is we start to introduce a lot of other SHAs into the system. To have to go and traverse and check the SHAs of every single of a billion individual fragments is not possible. It's simply not tractable to do and try and do these integrity checks millions of times a second. And so what we've started to introduce, and what's really powerful, is a deeper understanding of the dependency of data and how it correlates not just across fragments, but within an individual component. And so what we've introduced is the notion of hierarchical PSHAs as well, and been able to link these together and say that, well, we know, for example, that if the PSHA for all of December of last year matches the PSHAs that we expect, we don't even have to actually traverse down into those trees. We can simply short circuit the entire computation. And when we start to roll this up into higher and higher structures, we find that you have to explore very little portions of any set of pipelines, any set of transformations and the data flows when the PSHAs are matching. It really is only when there's a mismatch in PSHAs that you have to go deeper into these trees and the dependency graphs to see what doesn't actually match. And so this is a really nice ability to then have the system run incredibly efficiently and only have to do deeper exploration when you know confidently that work is going to have to actually be done. So that's how we tackle the detecting of changes very efficiently. The second piece that we talked about running efficiently at scale is how do we do less work? And less work boils down to something really simple, which is first, we want to do smaller jobs. If we can send smaller jobs, they have a tighter mapping to the data that has changed itself. The second piece is deduplication. It's incredibly important to never run the same piece of code on the same piece of data. If we're able to do that, we can make our systems run far more efficiently. And we'll talk a bit more about how we do that later with intelligent persistence. And then the third, that's also related to intelligent persistence, is we keep copies of all of our intermediate data that's still in use. By doing so, this allows us to guarantee that we won't run the same piece of code on the same piece of data. And moreover, if we ever want to branch off a piece of data and go somewhere else, we can do so very easily. So let's go into even more of detail now on how do we do the right kind of work. So for those of you who have run Spark clusters in the past, you've seen a lot of this notion of startup times before. We usually start with wanting to run Spark. We run a lot of it on K8s clusters. To create a K8s cluster from the ground up usually takes around 15 minutes, and that becomes our execution plane itself. When we start to think about how do we speed these things up, is, well, we know we can add VMs and individual nodes to Kubernetes in 2 to 5 minutes, and this really depends on the speed of the cloud itself. When we then get to the notion of how do we actually create Spark clusters that can do work, well, when we start to layer in those Spark clusters, we know we can spin up in Kubernetes individual Spark cluster in 30 to 45 seconds, assuming we already have the nodes and the capacity. Then when we start to think of how do we even make things faster than that, we know that if we run a Spark cluster in local mode, which is it only has one driver, one executor, and they're really the same thing bound together, we know we can get that in 10 to 15 seconds. And then we even know that if we run a Spark job on an existing cluster, the overhead and the startup time is very minimal, just a couple of seconds. And so when we take this backdrop and apply a reduce, reuse, and recycle mindset to how we send the right work to the right systems, one is we try and reduce our work into smaller jobs. We can run work on individual partitions so that we're not having to stream in huge volumes of additional data that we have already done the work for. Because we can because we can detect changes on individual partition level, the system can be smart enough to say, oh, I only need to update one of 100 partitions, so let me just send a small number of jobs in. We also know that by reducing things down when we only need one executor for the job, since we're aware of how much work has to be done, we can compact those down and run a local mode Spark cluster. When it gets to reusing resources, we try and reuse Spark clusters and infrastructure where we can. If we can maintain a gRPC connection and send multiple jobs to the same Spark cluster, we get a vastly more efficient spin-up time, and the system itself just runs far more performantly. Thirdly, on recycling, we use dynamic numbers of executors for every Spark cluster, and we auto-scale the Spark clusters and dynamically create the Spark clusters as well as the Kubernetes nodes. So this entire thing essentially ebbs and flows based on the demand itself. So this all in all together really helps us make sure that at a control plane level, how does it send the right kind of job to the right piece of Spark infrastructure to really optimize and get us the efficiency and performance that we're looking for. Now, Spark isn't right for everything. So we have also introduced this notion of these high performance lightweight workers. And we do send work to this pool too. These are fully isolated, non-distributed workers, but they're great for these really small jobs where the spin-up time is less than 100 milliseconds because the job itself may not even last for a second. And we use these in a similar auto-scaled, highly reusable fashion that also operate on the worker or on the executor plane as well. Now, let's talk about the last piece here that really quickly about running at scale, and then we'll be kind of wrapped up on the autonomous part. There's 4 elements when it comes to workload and capacity management. First piece is becoming very priority aware. Not all pipelines and data flows are the same. And so understanding the priorities of even and output pieces of data. If you have a high priority set of data that's feeding a machine learning algorithm or an executive dashboard, understanding that that data is higher priority and being able to dynamically shift the resources there appropriately is incredibly important. So we've introduced a priority construct that actually allows explicit and inferred priorities based off of the importance of different components. The second thing we've also introduced is a dependency-aware part of our system. For example, you may have some work to do to process, let's say, an hourly roll-up of data at stage 3 of a 5-stage data pipeline, but you may also have data that's just around the corner. It's already at stage 1, and the system itself may end up being better off waiting for 30 seconds for that piece of data to arrive as it will run just more efficiently. So being dependency aware is incredibly important to your workload and capacity management. Third part around being capacity aware is the control plane itself has to actually understand how many resources it currently has available, how many resources would be needed to service all of the pending work currently, as well as the limits in the environment. So the control plane itself has configurable auto-scaling limits that it's aware of. So it knows if it were to send all the work out right away, could it even be done? And as a result, then, because of this capacity awareness, the control plane won't send too much work to the execution plane and swamp it and overwhelm it unless it's actually capable of doing the work itself. So that's really important. And then lastly, obviously, is managing of the capacity itself. We run a lot of auto-scaled on-spot and preemptible instances. This gives us great cost reduction, but it also gives you no guarantees of availability, which generally means you need to be able to fall back on on-demand and other instance types. But you also have to then have really intelligent retry logic, which the control plane is fantastic for when you want to categorize things as, did this job fail because it was bad code or the data was bad, or is it just simply because the VM and the node went away, and as a result, it's safe to retry, just put it on a different node. And so putting in those intelligent layers are pretty important. Okay, so that was the deep dive on running efficiently at scale, and gives you a really good sense of how do we actually drive for autonomy here. Now, the last part that we're going to talk through is around this notion of intelligent persistence. And this is what I highlighted earlier as really one of the areas where we spend the vast majority of our time as data engineers, is frankly chasing this notion of how do we not repeat ourselves, and how do we never run the same piece of code on the same piece of data. So if you remember from our previous diagram, one of the other things we do track about a fragment is the location. And that's because we'll actually store that data itself inside of S3 or Azure Blob Store or Google Cloud Storage. And we'll store these as snappy compressed Parquet files. And this actually gives us a handful of really interesting benefits when we start to apply some more intelligence to this. First one is we have zero operation pipeline copies. If I copy a pipeline and I then try and rerun it or have it catch up, all of the same PSHAs are there. The definition of that pipeline itself, it's still the same code running on the same pieces of data. And as a result, all that data already exists inside of my storage layer. So I don't have to actually do anything, any new work. This also gives me really incredible data deduplication across dev stage and prod. It's very, very hard to actually be able to trust prod or dev data in staging and prod and vice versa. Yet, if you have the integrity check down to what is the actual code running on the actual pieces of data, I can literally copy a production pipeline, take it into my dev environment, work against it, but I already have all of the data there. I can submit my code into a staging environment, have it actually run the code I want in production. And by the time I promote that code to production, all of the SHAs are actually there already. All of the data has been calculated, and I can get an instant deployment that's already caught up, that's already running as a result. The third benefit to this is I get really efficient rollback and restart. If I simply roll back to a previous version of a data pipeline, garbage collection doesn't happen until later on. And as a result, assuming garbage collection hasn't taken those old fragments of data, I can simply just repoint all of my pointers to the previous generation, and it's instant. Now last, and depending on your perspective, maybe most important, is the net result of this is we end up with faster, cheaper, and more efficient pipelines because we're never repeating the work. And when we look at what happens inside of most data pipelines today, is there's a tremendous amount of inefficiency and waste because we're just constantly reprocessing data. So this is a huge benefit for many. Now, when we think about the core tenets and how we actually deliver on this, there's really four pieces here. One is immutable fragments. We have to be able to guarantee that when we write data, that it's write once and only once. If it's a retry of a job, it has to write somewhere differently. And this allows us to be confident and safe that when data is written, that it won't change out from underneath us. The second thing is that we need idempotent fragments. If we apply the same inputs and transform logic to the same piece of inputs, that we will always get the same output. It needs to be highly predictable in that way. Third piece is that we need to be able to commit our changes. While we're generating large volumes of new data in our blob store, they in essence don't really exist until we commit those changes at a metadata layer to the control plane. And then we can also safely garbage collect data in the background behind the scenes. And these are really the core tenets that make this possible. Now, when we think about what we do on top of that, this gives us a really good visual as to how that works, which is, one, we can create content addressable storage, which is a really fancy way of saying we can use all of our metadata to reconstruct logical, sensible folder structures that make sense to us as humans that can point down to all this underlying data. And when the underlying data is stored in this blob store, because it's stored tied to these UUIDs and PSHAs, it's hard to make sense of, yet we can have multiple components pointing to the very same pieces of data because they can share that piece of data, because they're sharing code, because they're sharing inputs. So this helps us then create far more sensible folder structures that are tightly bound to the pipelines that are actually operating on the data. The second really cool thing that we get to do as a result is we get to have atomic lists, reads, and writes. Because of the metadata layer and how we commit this data, when we list data, when we list all of the underpinnings of data, we know definitively that the data can't change out from underneath us. And as a result, we get highly predictable reads that are reflective of the point in time of lists. And this gives us a great snapshot and ensures consistency in a massively distributed world that is otherwise very hard to accomplish. Now, when we take this and look at how does this actually for our users and our customers, how does this really manifest itself? Well, it gives us two things. One is it gives us this notion of a structured data lake, which is a product Ascend launched last year, which gives us access to all intermediate data for every stage of every pipeline. We expose this through an S3 compatible interface using a technology called MinIO that makes it look just like S3, but gives us dynamically constructed file paths that are directly aligned with the pipelines and the stages themselves. This is incredibly powerful because we can now put a Jupyter notebook, a Presto cluster, a CLI, anything that talks to S3 can now directly access all of the underlying intermediate data as part of any data pipeline, which is incredibly powerful. The second thing that we've opened up and used all of this metadata information for and this intelligence persistence for is queryable data flows. One of the hardest parts around data engineering has been this ping pong exercise of going from constructing of a data pipeline to exploring and querying the data, figuring out what the next stage should be, and then flipping back to what that pipeline architecture should look like and trying to build it there. And this becomes a really slow, arduous process. Yet with queryable data flows, because we have this intelligent persistence, we can actually now hybridize the pipeline and data warehouse method and dynamically query each and every single stage of a data pipeline as if it were a table. And we get the benefit of doing so by using the same Spark infrastructure that we have today, that's auto-scaled, that's performant. Moreover, we get all of the control plane benefits around deduplication. We get to persist our historical queries. We know whether or not a query has been run before and can just instantly return the results. Or if the inputs for that query have actually changed since the last time we ran it, there's intelligent change detection, and we can notify the user and they can rerun it if they so choose. So again, all of this comes down to those core principles of if we can safely and intelligently persist data, we don't have to run code more than once ever on any piece of data, and all of this starts to become very, very possible. Okay, so bringing all of this together and pulling it back up here, just as a kind of a quick reminder, this is really how a lot of the infrastructure at Ascend looks. I'm guessing many people have similar kinds of architectures inside of your own companies. The control plane has a lot of complexity that we didn't go into around just the security model and authentication, authorization, but we won't worry about that for today. I think it's more important to pop up even higher up here and give us all a bit of a recap, which is when we think about declarative pipelines and intelligent orchestration, the really key takeaway hopefully for folks is this proper separation of logic, control, and execution. The logic plane is where we define the what. Control plane is the system that can intelligently determine the how, and the execution plane is the one that gets to actually do the work. And so the core tenets of that and how this really starts to look goes back to those notions of data awareness, autonomy, and intelligent persistence. And with those, this is how we can really build the backbone of the intelligent control plane that lets us architect these declarative pipelines with far less code and much less developer burden. So with that, I'll thank everybody for your time today. I think a number of folks have been submitting questions into the channel, which I'm looking across the table at the team, and I think we've been trying to field as many of those as possible. For those who really like the conversation, we welcome all the feedback. If you're interested in a 30-day free trial of Ascend, just head to our website, and there's a link on the homepage where you can head to get started. And if you're interested in a more deep dive demo to see the product itself in action, we also have a link there, and we would love to hop on a call and show you more. With that, I think I will thank everybody for our time today. Thanks so much.